without being a graphics expert. Suddenly, if you knew programming, if you had some concept of parallel programming, maybe even some computer architecture, you could come in and program something that would work really fast. You could take a traditional C program, or any program, port it to C, and then port it to CUDA. And I'll give you an example of what CUDA looks like later, but it looks basically like C with some extensions. And what happens is there's a specialized compiler that then goes through and parses it out and breaks it into a C portion, or a CPU portion, a GPU portion. It does all the necessary state and glue and everything to program the GPU and set it together so they just cooperate. And all the really icky details happen under the hood, and you don't have to concern yourself with it, while still giving you enough flexibility over what's going on that it's not overly dumbed down. So I've been talking a lot about threads, blocks. This is basically CUDA in one bit. So you've got your individual thread, just like a CPU. It's going through and doing some track of work. Threads are grouped together in blocks, and really within that, kind of within warps, but I won't go into warps a lot. It's kind of a weird thing. But these blocks all operate together. So it's basically 32, 64, 128, whatever you specify, a whole bunch of threads all doing exactly the same thing. They might be operating on slightly different data, but they're doing basically the same thing. They can take some, in modern hardware, they can take some different branching, but they're all essentially following mostly the same code. Although they can definitely do have some inter-thread communication, synchronization, stuff like that. And they can have barriers between execution, again, using semaphores like we talked about earlier. There are different kinds of barriers. Again, I'm not an expert on this, so I'm not going to go a lot into it, but this is kind of the high-level takeaway. Then these blocks are essentially, a kernel is composed of a whole bunch of these blocks. So when you launch a kernel, you're going to say, I want to launch a kernel that's going to have, X number of threads overall, and I want the block chunking to be on this boundary. So 16, 32, 64. I'm not sure if you're constrained to power of 2 or not. It would kind of make sense if you were, but I'm not sure. And then you can have different kernels that are communicating. A kernel is essentially a function in this parlance. And they can be synchronized, pass information back and forth between them, so on like that. Threads have local per thread memory, obviously registers. Each thread has its own set of registers that it's working with. And also some just local memory that's not just registers. Blocks, they actually get a chunk of shared memory. And we talked about the shared versus cache system earlier. But a lot of times it's very helpful to be able to have all of these threads to be able to have some sort of memory that's just shared within this block. And then finally, the kernels all communicate with a global memory, which is basically VRAM. Although, if you're a little bit twisted and crazy, you can use system memory and go across the bus for this. You're going to run really slow, but maybe you have a good reason, I don't know. Okay, so this is basically what your traditional C algorithm would look like for doing summation. Really simple, just loop over this array, multiply something by one value, add it, done. Basically running time event. This is the CUDA version of it. Very, very similar, but like I said, with some extensions. Basically, what's going to happen is this function is going to be run individually by each thread, and each thread is basically going to say, who am I? And then once I know who I am, that tells me what work I'm going to take, what my part in this computation is going to be. I do some small part of that and return. And that's basically it. And then down below, when you launch it, you basically say, I want to run this number of blocks with this number of total threads, and there we go. Actually, that's not, that's basically it. So if you already know C, it's not a big stretch to get to here, which is, it might sound like, all right, sure, cool, now, but at the time, that was big. Because no longer do you have to be a complete, black belt in OpenGL to get this done. Obviously, you can't do everything on the GPU. The GPU is simply not good at everything. It's great at parallel stuff. So that's why C is so nice for this, because you can have some functions that will run on the CPU, some functions that will run on the GPU, and they can be interleaved. So you can do all of your setup, any sort of processing that needs to be serial go on, have the GPU run a bunch of things, and then come back to the CPU for anything that has to be serial, and it's a very natural way to break things up. Now, as I hinted earlier, you don't really want to do a full trip on the bus for all of your data, so you still want to be careful about what data you're transferring back and forth between these steps. But if you can basically read back just a tiny little bit on the CPU to figure out what you need to do next, and then send some stuff on, or maybe change the setup of what you're going to do with the CPU, reprogram the GPU, so to speak, and then go on, that's a really standard control flow for this sort of programming. So that's kind of today. This is where things are moving now. Instead of it just being, CUDA's this neat thing that NVIDIA's done, and that's great if you have an NVIDIA card, it's moving to be a much more general movement within the computer industry. So it's no longer just NVIDIA. It's NVIDIA, AMD, Intel, who knows, maybe ARM's going to get into it. And there's a lot of publication out there, not just research now, but textbooks, general things telling you how to use this. And also languages, so it's moved beyond just C. I'll get to that in a bit, but there's basically a lot more support now for doing this kind of thing than there was before. You can actually do CUDA work on a whole range of hardware. When I first hired on NVIDIA, one of the questions was, do we make CUDA Quadro only, or do we make CUDA available on every machine out there that's got the hardware available? And the decision was made that, yeah, it would be a nice selling point for Quadro, to be able to say, like, buy Quadro and you get this, but it's a lot more cool to say to people developing applications, hey, there's 200 million of these things out in the wild, go program for it. And now that other people are stepping into it, and it's not just NVIDIA, now it's like 1 billion, 2 billion of these things are out there in the wild, go program for it. And so it becomes really obvious if you're a game programmer, or if you're any sort of programmer who needs a high amount of throughput, that you can write something and it's probably going to work at your client's site. I talked a little bit about earlier, and I'm not going to go into a lot of detail about high-performance computing. This is really changing the way high-performance computing and supercomputing work and what they can do. I think that's probably all I'll say about it right here, unless people have questions. And this is just kind of a sampling of the sorts of problems that people are really now today tackling. But again, I'm just... so this is kind of where things are today and where they're going in terms of the sort of support out there. So, like I said, it started with C. With Fermi, we can also do C++. You've got OpenCL, which started with Apple, and it was basically, Apple said, well, I know if we don't do something, Microsoft's going to have their version, and it's going to become the standard, and and so Apple really started pushing on this because they didn't want to be tied to CUDA. Like, they want the freedom to ditch NVIDIA and move on to Intel if Intel becomes better. And it's unlikely Intel's going to really embrace CUDA because it's ours. So they wanted a vendor-neutral approach, and that's where OpenCL was born. Direct Compute is Microsoft's way of saying we want a vendor-neutral approach, but tied to our operating system. So we've got Direct Compute. CUDA's moved to Fortran. Well, I think we've had Fortran for a while, but that sounds funny until you realize that a lot of the people doing scientific computation are math people. They're physics people. Fortran, for whatever reason, sticks around for these guys. And so it's important that we have stuff that works fast in Fortran, so there we go. And now enough people are wanting to use CUDA and other places that whatever your language of choice is, it's starting to get to the point where you can do it with CUDA. So those are just a couple of the samplings of where people are using it. And obviously, it all works in an NVIDIA GPU. I think I'll leave it at that. There are differences. CUDA is not the same as OpenCL. OpenCL is not the same as Direct Compute, although they're more similar.